Hello everybody, we are Group 2 from Section 0104 and we'll be presenting our final concept selection on buttoning assistance. To introduce you to our topic, basically we've identified this problem among people with dexterity issues. They're having problems buttoning their shirts. And among Americans, there are about 52.6 million Americans that have dexterity disabilities, and about 60% of those individuals are above 65 years old. To make sure this problem was worth pursuing, we sent out a questionnaire to the Benjamin Gaither Senior Center, and we asked them how difficult did they think buttoning a shirt was. We had a very small sample size due to COVID-19, but the response was basically that it was moderately difficult, despite them not having any disabilities. We also looked at some of the current solutions out there. This was a good example of one of them. It consists of a loop, a wide grip, and a zipper hook. And there were a lot of complaints about this solution, and among them were a flimsy or weak loop. It would break easily. It was not very usable for customers with one hand, and also it didn't work with jean buttons, although this was not a real consideration for us. So once we did that, we could start preparing for concept generation. And to do that, we identified some customer requirements. First thing, it has to be safe to use and comfortable to grip or hold, because this is for the elderly. It should also be able to work with different button sizes. You should be able to use it with just one hand, and not a specific hand. It shouldn't use much strength to operate, and it should be easy to understand. And some of the critical product functions should be that it should secure it to the user's hand. You should also be able to secure the button in the device easily. You should also be able to guide the button through the hole on your shirt, and also prevent the buttonhole from moving too much. We also developed a list of engineering characteristics. Among them are like cost, strength required by the user, weight, etc. And from this list, we narrowed it down to a few critical ones, which are in the strength required by a user, ease of use, reliability, and performance. Those were the most important ones, and we'll be using those for the analytical hierarchy process, which we'll explain later.
We then started with our concept development, and our concept generation started with the 635 method. And with this, we were each able to generate 9 concepts for each function, and we chose what we thought were the three most critical functions, which were secured to the user's hand, secure the button in the device, and guide the button through the hole. And for function 1, mostly our ideas mostly involve handles, straps, and variants of those, with a lot of modifications to grips and straps for hands and wrist straps. Ideas for function 2 involve different kinds of hooks, clamps, clips, and even magnets. Out of everything, this function was the most broad and diverse in terms of generated concepts. And for function 3 is where we started thinking about mechanisms for the actuation of the device, which also had a great amount of variety, and this included push, pull, rotational mechanisms, gears, and motorized mechanisms for guiding the button. After we generated our concepts, we used a morphological chart to combine our ideas into some feasible design, and the different color highlights shows concepts that could be tied together for one complete design. To further narrow down our concepts, so we eliminated unfeasible concepts that wouldn't work after our decision criteria and target group. Homework 4 also helped us narrow down from 27 to each of our 10 concepts, and we discussed what would be difficult to implement. One of the things was electromagnets. It would be difficult to implement along with being expensive. It would also produce a high level of complexity, which affected our customer. But we didn't completely rule out magnets at this point. We also eliminated things that completely encapsulated the button because this would be very difficult to fit through the hole, as well as advanced sensors. Using advanced sensors would greatly increase the cost of the device in addition to being difficult to implement. We considered gyroscopic sensors, for example, just to stabilize the user, but this wasn't feasible. We then moved on to decide what universal components had to be on the design. We decided that clamping of the shirt was necessary because if the device itself didn't clamp the shirt, then the user would need 2 hands. And since one of our main goals was to make the entire process easier, we decided that this was necessary. We also thought it was necessary that a user guides a part of the device through the buttonhole and attaches it to the button. When we thought this through, we realized that it would be too complicated to have the device detect the button and the hole. There was just too much error for it, and performance was a big decision criteria for us. And we also thought that a loop similar to the existing product was essential. Feedback from current products showed no issue with the customer performing this task with the loop and hook design. and we used paper clips ourselves to test this, and there wasn't really any difficulty. We then decided to narrow down into 2 concepts per each person in our group, and we came up with rotational mechanisms with and without a power source, lever mechanisms. We also have push and pull and more rotational mechanisms, and some rigid arm mechanisms.
So the 5 concepts that we ended up using for our Pew chart analysis were the rotational mechanisms with and without a power source, a clamp lever mechanism, a push-pull mechanism, and then a rigid button arm with powered movement. So some of the key similarities between these, as you can see, I recorded a video of myself buttoning my shirt with a makeshift button hook made out of a paperclip. So 1, the user must guide the device through the buttonhole and onto the button, and 2, all concepts must somehow clamp onto the shirt since we're considering concepts that only need one hand to use. As you can see, I have to use 2 hands to do this because one of them has to grab the shirt. So the first concept was a rotational mechanism without the power source. This uses a spring inside to cause the arm to retract when the user provides a slight force to it. As well, the prongs will expand and hold onto the shirt. The rotational mechanism with a power source. So this one is similar to the last one, however, it uses a motor instead of using the user's rotation, and that motor causes the button arm to retract as well as the clamp on the shirt. The clamp's lever mechanism, so for this one the user has to clamp onto the button using the lever arms, and then this clamp also provides a force onto the prongs. The user must then pull it through the shirt. The push-pull mechanism, so basically there are 2 arms that work simultaneously to push the button through the hole while pulling the hole over the button. And then the rigid button arm with powered movement. So this button arm does not bend, it's not flexible, it just retracts into the device itself. So the key distinctions here, we had either pressing button versus having to rotate or squeeze the handle. We were using motors versus springs or leverage. A lot of it comes from the button arm, whether it has to coil up or whether it gets to be rigid. And then the buttonhole movement, we had prongs versus clamps. So the Pew chart analysis removed the clamp, lever, and push-pull mechanisms from our final decision, which left the top 3 choices. We had the rotational mechanism without the power source, rotational mechanism with the power source, and the rigid button arm with the powered rotation. So looking at our rotational mechanism without the power source, we have the handle, we have a main spring, we have inside the device the user inputs the slight rotation to cause that spring to slip and cause the button arm to come in. Some advantages, there's no motor, however, it does require movement from the user and it would be difficult to use repeatedly. The motor, the rotational mechanism with the power source, so this one's similar in that you still have to wrap the button arm up around the cylinder, however, it's using a motor to do this instead of using the user rotation and springs. Little strength is required for that, it can be more compact, however, the material must be strong but also flexible since it's being wrapped up but also required to be somewhat rigid. And also the motor obviously increases the weight and the size. So lastly, we have the rigid button arm with powered movement, where the button arm is retracted by a rack and pinion and a motor, and the shirt clamp is also powered by the same motor. So the advantages, it's strong and it's durable because it's a rigid arm, it doesn't have to be flexible. Also, little to no strength is required from the user. It's also reversible to set up for the next use. Since we're using a motor, we can have it go both ways. However, the motor and the battery are more expensive and they're heavier.
Alright, so moving on to the final concept selection, we ultimately decided on the rigid button arm with powered rotation, concept 3. So our overarching goal here was to maximize the effectiveness of the tool in terms of buttoning shirts. And our most important decision criteria, as you can see below, were strength required by user, ease of use, reliability, and performance. So we chose these after seeing our results from the design specification matrix and house of quality. And those were focused ultimately on our most vital customer requirements. So that would be for the elderly and disabled population. And so based on our initial reciprocal matrix, we were able to determine the weights for each of these design or decision criteria. And we found that ease of use and buttoning the shirt was the most important out of these, with performance of the tool coming in second. So now here's a summary of our analytic hierarchy process. So through our comparison, we saw that concept 3 was definitely a clear winner. So concept 3, the rigid button arm, had the highest level of expected performance, most ease of use, and also the lowest strength required by the user in order to operate it. And that makes sense as it's one of the two concepts that has a motor. So meanwhile, concept 1, the rotational mechanism with no power source, took the prize for reliability. However, it underperformed in all the other categories. And then concept 2 was kind of in the middle for all of them. So overall, you can see the aggregated weights here show that concept 3 is by far the most effective tool in our estimation. And going down to the consistency scores, you can see they're all much lower than the critical value of 0.1. And that shows basically that our comparison process was rational enough to where we could make a good conclusion.
Moving on to the human factors, we consider the effects of population characteristics on our top concepts, one of which was the level of dexterity needed. Much of our design depends on how well we believe the elderly, which is our target audience, can use their hands to operate the device. If we assume low dexterity, that translates to greater mechatronic assistance. And another thing was the cognitive ability. There's a high level of focus that's needed, and using two hands is a lot more difficult. So we want to alleviate this and minimize this, which led us to the rigid arm design. We also considered the interaction between the user and the device. The final concept needed to be very user-friendly, and rotational movements needed from the user would be more difficult considering our population, and pushing a button is a lot easier than providing rotational movements. Some factors that influence user accommodation were the physical limitations, for example, shoulder and elbow movement, elderly restricted to wheelchairs, sensory limitations such as visual impairment, users with only one functioning hand, and the ability for users to use the device intuitively without struggle. And all of this led us to the rigid arm design.
We will now discuss the final concept design. The user first pushes the button arm through the buttonhole until the clamps reach the edge of the shirt. They then clamp the device onto the shirt by pulling the button located on top of the device. The user then places the button loop on top of the button and retracts the button arm into the grip by using the forward and reverse button located on top of the grip. Once the button goes through the hole, the user then releases the clamp using the clamp release buttons located on either side of the device and moves to the next button. Key features include the rack and pinion arm for the button arm, as well as the teardrop shape of the button loop and the hollow grip, which is used for housing the retracted arm. This side view provides visual representation of the clamp's orientation compared to the button arm and the button loop, as well as locations of the clamp release levers and the switch located on top of the grip. These final sketches show the mechanism used for the clamping device. The way it works is that the user pulls the clamp button towards the grip, which then raises the lower jaw and comes in contact with the upper jaw. The clamp button is held in place using bars with teeth on both sides that stop the button from returning to its original position. When the user is done buttoning their shirt, they then release the clamp using the release levers on both sides, and then the coil spring located in between the clamps allow the clamp to go back to its original position. The first reason we chose this design is because it completes the goal of assisting the user with fastening buttons to their shirt or coat. We use button loops instead of hooks because they're less likely to snag in the buttonhole, and they also have a larger range of buttons that they're compatible with. We use a linear grip instead of a perpendicular on the device because linear grips provide a larger range of motion, and they also provide more control on the device. We use rack and pinion gears instead of threaded because they're less expensive and easier to manufacture and place into the device. We decided to clamp on the shirt instead of hooking the buttonhole because clamping onto the shirt opens up the button without restricting movement through the button by the arm. We use motor assistance versus manual motion because it allows the user to complete the task with the least amount of manual motion possible. Some strengths in our design include gear teeth being located on the side of the rack and pinion arm, which stops snagging of the arm within the hole of the shirt. There's also the grip ergonomics and comfort, which include the shape of the grip as well as the fins, which prevent slippage of the user's hand. Also, a simple device activation through the use of a rocker switch will allow the user to easily understand whether they're going forward or backward. The button arm housing is also an improvement because it allows for the arm to retract without scraping against the user's wrist. Some weaknesses we need to improve on include clamp internal mechanisms, which may be complex or cause the user discomfort to activate. Also, the battery size and location, which includes whether or not to use rechargeable batteries and what size or weight they may be. This concludes our final concept selection presentation. More information can be found on the supplemental PowerPoint submitted on ELMS.